Hello.
Can you please take your time to explain to us, okay?
Okay.
Go ahead. We are listening.
Okay, so a mirage is an optical illusion in which the image of the sky appears on the ground as pool of water.
Okay.
On a hot day, pools of water is seen on a long stretch of road. This occurs because there are hot layers of air near the hot road and cooler layers of air higher up. A ray of light traveling through these different layers of air is gradually refracted more and more towards the horizontal.
Okay.
Eventually, it meets a hot layer near the ground at an angle greater than the critical angle and therefore
Okay.
undergoes total internal reflection.
Okay.
Yes.
Okay. Are you done?
Yes, please.
All right. In fact, thank you so much for the contribution. Okay.
Yeah, very well.
So appears as a pool of water on the surface of the road. Okay. Do I have another lady to also share with us what she learned or you also read about the concept of mirage formation? Another lady. It is the lady's turn. And Zainab contributed perfectly. Okay. So I have Yasmin and Michelle. Wow. Okay. Yasmin first, and then when she finishes, Michelle will also come in. Yasmin, go ahead. Yasmin, can you hear me?
Yes, sir.
Go ahead.
Okay, so a mirage is like an optical illusion, something that is not real but is actually happening. So it
Okay.
is caused by when light bends, when it passes through layers of air of different densities and temperature. So during hot weathers or when the temperature is hot,
Mm-hmm.
hot hot air is formed around the ground part of the earth, and this hot air is less denser than the cool air that is formed at the upper part of the earth. So when
Mm-hmm.
light passes through these layers of air, it bends because the air at the upper part is more dense. So it's
Mm-hmm.
causing this mirage that we see.
Mm-hmm. Okay. Where? Causing this mirage that we see at where?
Maybe in pools or on deserts.
Or on the surface of tarred roads.
Yes, please.
Okay. Michelle, what do you have to add?
Okay, please, as already said, the mirage is an optical illusion, and this happens when it's really hot and the ground heats the air just above it. Then the air near the ground becomes much hotter than the air higher up. And since
Okay.
light bends when it moves through air layers of different temperatures, it bends upwards before reaching the eyes. So basically, your brain thinks the light is coming from the ground, like a reflection, and what you see looks like water or a shiny surface on the road or on the desert.
All right. Thank you, Michelle. The gentleman, it's your turn now. Gideon.
So please, mirages are formed
Hey, Gideon, your network. Your
when
net.
the weather gets really hot, which heats up the ground.
Mm-hmm.
Hello, sir.
Yeah, I can hear you
Hello, sir.
now.
Can you hear me now?
Yes.
So please, the mirage is formed when the weather gets really hot, which heats up the ground and also heats up the air directly above the ground. So when
Okay.
the light coming from the sun, instead
Mm-hmm.
of going straight, the hot air above the ground bends the light towards the eye. So the eye always or usually sees light traveling in a straight line. But then when it sees the bent light coming from the ground, it creates the illusion that there is water on the surface of the ground. Meanwhile, it's actually the reflection of the sky.
Okay. Okay. Frank.
Um, so we have two types of mirages. That's the inferior mirages and the superior mirages. The
Okay.
inferior ones are the ones that the image appears below the real object. That in
Mm-hmm.
that one, the hot air is above the colder air, which is less dense than the colder air. And
Mm-hmm.
the superior mirages, they have the hot air that is the air, the cold air that is above the hot air. That's known as a temperature inversion.
Okay.
In superior mirages, they mostly happen in polar regions. For
Mm,
example, like a distant shoreline that may appear to tower and look higher than it really is.
okay. All right. Thank you so much for the wonderful contributions by all of you. I have a question. My question is that please mute yourself if you are done contributing, okay? Can you please mute yourself if you haven't muted? Quickly check and do so. Ohenebia, I think your mic is on. Ohenebia. All right, thank you. Do we know the saying that the higher we go, the cooler it is?
Yes, sir.
Yes, sir.
The higher we go, the cooler it is. The source of heat on the earth is from the sun. The sun is actually in the sky or in space. So if there is a saying that the higher we go, the cooler it is, it sounds a bit confusing in the sense that once we are going up, it means we are going to the direction of or the location of the sun. So why is it that instead of us feeling warm as we go up, there is a say that it's rather cool? Can somebody explain? Gideon, you have spoken. Let others also contribute. Okay. I want somebody to explain why. Because if I'm going up, because it's like a source of fire. If I'm going closer to the source of fire, I must actually feel the heat of the fire source. But rather, in this case, I'm told it is the cooler it becomes rather. Frank, you have also contributed. Let me call somebody else and then.
Sir, please, I don't really get the point.
My
Like,
question is,
you are
my
getting
question,
closer to it or up, like going up. I don't get it.
the sun is in space, okay? So if I find myself on the surface of the earth and I'm going up, then I'm going to space, isn't it, Biney?
Yes, sir.
So if I'm going closer to the source of heat, I must feel warm. But they are saying that as you go up, the cooler it becomes rather. That's my question. Biney, are you okay?
Yes, please.
Let me see if somebody else. Saki, can you explain?
Sir, please. In the atmosphere, there's a less presence of oxygen and more presence of greenhouse gases such as carbon dioxide, which trap the heat. So as you are going up, the concentration of those greenhouse gases to also reduce. So
The heat is not trapped. The heat, it actually traps some dangerous, okay, gases, I know. But then the heat comes to the surface of the earth. That is why we feel that warmth. The sun, the heat produced by the sun is the source of heat on the surface of the earth. So the heat is not totally absorbed. Are you okay?
yes, sir.
So if I'm going up, getting closer to the sun, I must feel that warmth. So you still have something to say about the question? Saki. Okay. This guy's hand was up. Frank, you raised your hand earlier.
Sir, please, I think it's because there is not that much substances to conduct heat in the sky, but on the ground, on the surface of the earth, the ground like collects the heat, which makes the surroundings like hotter than the atmosphere.
Okay, you are making some very good points. Yes. Another hand, this is from Elikem. Oh, Ablina, let's give the chance to Ablina to also contribute. Ablina, I'm listening. Oh, Ablina, your hand was, or it's still up. Okay. Gideon. Gideon.
I think the reason why the higher you go, the cooler it gets is because you are going. You see, the Earth's core produces some heat, some level of heat. So when you dig further down, you realize that the heat level becomes more. So the higher you go, the farther away you are going from that heat that's coming out of the Earth's core. That's why I think when you go higher, the
No,
heat
the
becomes.
heat, as I said, the heat we feel is from the earth, is from the sun. It's from the sun, not the heat within the earth crust or the core of the earth. Okay, so part of it is what is said by Frank.
Frank.
Air itself is an insulator. Air does not conduct heat as solids do. Okay, the heat we feel from the sun is actually due to radiation. In radiation, Alvin, please mute yourself. With radiation, it is not the molecules of the material which transfers the heat. Okay, but you see, because the air is an insulator, because of the wider gap between the air molecules or particles, it becomes an insulator. Now, when the air does not directly, or the heat does not directly affect the molecules of the gas in between us and then the sun so much. But when it gets to the earth through radiation, okay, because, please, I'm coming. All right. Because there are materials which can actually absorb heat from the sun, they get heated, and through radiation, we could also feel the heat absorbed by these materials. Now, as we move up, these materials are not there to actually pick up the heat from the sun direct. Okay, and that is basically the reason for saying that as we go up, the cooler it becomes. Materials. Oh, Alvin. Oh, today, please, when you join, quickly mute yourself in order not to distract. So part of the explanation is what is given by. Now, this is the sun. which produces the heat energy? Jackson.
So,
Yes.
please, I want to ask if I could say it this way.
Okay.
So, materials themselves, their surfaces emit, reflect light.
Yes.
So could I say because of the present, like the reflection from the surfaces of the materials
material.
around us. So,
Exactly.
and as you go up, like say the sun aren't.
Yes, you are right. Okay, it's the same explanation given by Frank and then myself. So as we go up, these materials wouldn't be available to absorb in order to reflect the light. Do we also know that equally, the higher we go, the lesser the concentration of oxygen we breathe? Do we know that as well?
Yes, sir.
Can somebody also explain that? Why is it that as we go up, concentration of oxygen also drops? A quick explanation to that, and then we move on. Ablina, or Ablina's hand is not up. Okay, Frank.
Since plants give oxygen,
Exactly. That is, it's okay. You are correct for 3 points. Okay. So it's because as we go up, plant species reduces. And if there are no plants, obviously there wouldn't be oxygen. So this is the surface of the road. Because of the radiant energy from the sun, the road surface with stones, gravels, okay, and then sun absorbs it and becomes very hot. So the surface of the air layer around the surface of the road becomes hotter than the layer of air above. So I've divided this into layers. 2, 1, 2, 3, 4, 5. So as we go up, the temperature of the air drops. The highly temperate area, or the air layer with greater temperature, becomes layer 1. Layer 2 would have lesser temperature compared to 3, on and on and on. So as we go up, the higher we go, the temperature of the air also drops. Now, temperature of the air also accounts to or reflect in the density of the air. Okay, hot air has less density. So the density of the air layer here will be less than the density of the air layer 2. 3 will be greater, 4 will be greater than 3, 5 will also be greater than 4. So as we go up, temperature drops, okay, temperature drops and density increases. Okay, the higher we go, the lesser the temperature, and then the larger the density. Please, are you taking notes of these points? Because the sun would heat up the surface of the road, okay, and then be reflected or would affect the next air layer. So the higher we go, the lesser the temperature, but the higher the density. So when the ray from the sun passes through this layer of different temperature and densities, so that the light coming from the sun passes through air layer with greater density than the next layer. So this satisfies one of the conditions for total internal reflection, that light must travel from higher density to a lower density. So 5 is denser than 4. 4 is denser than 3. So as the air layer, the light passes through this air layer of different densities, okay, they get deviated. They get deviated through total internal reflection. The next one would also deviate. The next one will also deviate. The next one will also deviate. The next one will also deviate. Now, when it hits the road surface, it will reflect. The order will change. Okay, this time around, the ray will be passing through or will be passing from lower density to higher density, and it will deviate towards the normal, towards the normal, towards the normal. So an observer at this point would see the deviated light. This is how the observer will pick the deviated light. And what he sees to be, what he will see will be the image of the sun, okay, which appears to be captured on the surface of the road at a far distance. So that seemingly pool of water the observer sees on the surface of the road is actually the image of either the sky or the sun. So the sun or the sky becomes the object, and the image, as a result of consistent total internal reflection of the light, an observer at a distance sees the image of either the sky or the sun as if it's a pool of water on the surface of the road. This is how total internal a mirage is actually formed, as explained by all of you. Okay, all right. Class, let me quickly drop attendance, then we continue. Give me a minute to quickly do that and then get back to you. We are going to continue with refraction of light in rectangular prisms. Okay, all right. So let's quickly continue with refraction of light in rectangular prisms. Refraction of light in rectangular prism. Saki.
Lebis, I have one last question about the mirage.
Okay, quick.
So, sir, please, the part that was hot, the place that we labeled 1.
Yes.
So, sir, please, that part is on the surface of the road or is beneath it?
It is the surface of the road. This, let me go back to Yes, this is the surface of the road. I believe I've indicated that here. One is the surface of the road. So when the ray incident on it, it hits up the gravels, the sand, okay, making one to be hotter or warmer. Are you okay?
Sir, please, so one is the actual road itself,
Yes, one is the actual road itself.
and the rest are the gravels and the stones.
The two is the, so one is the surface of the road, okay, with that air layer which is so warmed up. Two is the next air layer which is not so warm as one. Three is the also, so in between the sun and the road, it's been segregated into layers of air with different temperatures. Are you okay?
So, please, the air is what helps in the bending of the sun rays.
Come again.
So, please, the air is what helps in the bending of the sun rays.
What actually causes the bending? Yes, due to 8 different densities, and we can also say temperature as well. Are you okay?
Yes, sir.
All right. Alekem, please, let's be quick in our
Sir,
questions.
so what if the surface of the road is not actually a road, maybe something like ice or water, and then it's cold, the surface is cold, what will happen?
No, you see, whenever there is sunshine and even there is ice, it will melt. It will melt. So this bending thing, you see, formation of mirage always occurs during hot, sunny afternoons. You wouldn't find mirage on during cloudy days, no, or snowy days. It occurs during hot, sunny afternoons. Are you okay?
The one you told us to read, they were like, there are two types of mirage. The inferior one, which happens when the temperature is hot, and then superior, which happens when the temperature is cool.
We are judging it from only a mirage formation. Okay, don't just understand the basic concept under mirage formation and ignore the superior and then the inferior mirage. Just mirage formation, as we have all explained, right? Last question, Ernest, last question, so we can
Okay.
continue.
So, given the diagram you've shown us, let's
Yeah.
take for an example. We get into that area, like that scenario, but the place was contained. It was vacuumed. Will we still see the mirage?
If it's a vacuum, we wouldn't see
Pardon?
if it's a vacuum, we wouldn't see a mirage, because a vacuum is an absence of air. You get it? So it
Yes,
wouldn't
please.
occur in a vacuum. There must be air particles. All right, I think we can go ahead. I jumped my slides. Okay, so refraction of light in a rectangular prism. Please, this rectangular prisms or refraction in prisms, very, very important. In the lab, we most often use rectangular prisms and then triangular prisms. So with the prisms, we'll talk about rectangular and then triangular later. Prisms are, being it rectangular or triangular, are very, very important. Okay, after the lesson, I'll send you notes on uses of prisms or applications of prisms. Okay, but prisms are actually applied in several fields. Okay, in the sciences, in research, during physics practicals and all that. So I'll forward the applications of prisms to you after the class. So let's quickly look at refraction of light in triangular prism. Let me share an information with the class quickly on refraction of light in so give me a minute, I'm coming. I want to quickly upload I think stop. Oh, okay. Let's continue. I think I'll send you the YouTube video later. Okay. Class, I'll send you the YouTube video later. It wasn't saved. So I'll send it to you on the platform so that you watch it at your free time. Okay. So the prism, I'm sure some of you have seen what a prism is, being it rectangular and triangular prism. Some of you have actually seen it in your laboratories before. If you haven't, I'll still forward the video to the group so that you can, have a feel of how it looks like, okay? For prisms, they are very, very important because you'll be doing practicals on prisms. So this is the outline of the prism. Let's represent the height of the prism by the letter H. Light must be incidented at one side. So let's draw a normal so we can be able to measure the angle of incidence and then the angle of refraction. Angle of incidence and angle of refraction is always measured from the normal. And that is the main reason why you must always have this perpendicular line to the interface A, B, C, D. So a ray from the normal hitting the surface of the prism becomes the incident ray. Rays must be a bold line with an arrow in the middle. So this is I, angle of incidence. Since the light ray is traveling from air to glass, how must the light bend? Since the light is from air to glass, how will it bend? Will it bend towards it or away from the normal?
Away.
Away from the normal.
It's from air to glass.
Towards.
Towards the normal. Now, when the ray is coming out of the prism, because this time the ray is from glass to air, it must bend away from the normal. So this is how the path of the ray within the prism will look like. Now, if we extend the normal to DC, we have the the refracted ray, and this angle here becomes the angle of refraction. The angle of refraction. If we extend the original part of the incident ray. We realize that the original part of the incident ray seems to have been shifted by a certain distance. Yes, the ray is actually in this direction. The incident ray is in this direction. But due to the optical densities, its path has been shifted to this side. And then it is now coming out of the prism through this. And let me clear the emergent ray, because the emergent ray must be parallel to the original part of the incident ray. This must be parallel like this. So if you want to determine how much or how wide has the ray been deviated or been displaced, this distance from the second normal gives us the extent of displacement. So we call this distance as a lateral displacement. Lateral displacement. D. Okay. Now for what will be the name given to this angle between the original part of the incident ray and then the refracted ray? What name do we give to this angle here? What name do we give?
Angle of deviation.
Angle of deviation, because the incident ray has been deviated to a new path. Now, by vertically opposite angle, we realize that the angle of incidence I is equal to the angle of refraction R plus the angle of deviation, sigma, what I've represented to be the question mark sign, sigma. Therefore, sigma is equal to I minus R, which is angle of incidence minus the angle of refraction. So for refraction, this is how we calculate for the angle of deviation. Take note, angle of deviation. We did that for reflection. For reflection, we saw that angle of deviation is equal to 180 degree minus 2i, or 180 degree minus 2r, if you remember. Okay. Now, we want to use this experiment to calculate for something. Our interest here is to find the extent to which the ray has been deviated. So let's represent this point by the letter O. This is E. This is F. And then this is G. So when you look at the diagram, we have two right angle triangles in there. This side is perpendicular to the side DC. The original part of the incident light is perpendicular to FE. So this is also perpendicular. So we have two right angle triangles. We are going to use that for our analysis. So considering triangle OFG, and triangle OEF. Okay. AD is the same as OG. So if AD is H, then it means that OG is also H. Class, do you agree with me?
Yes, sir.
Okay. So we have the adjacent with the triangle OFG. We have the angle of inclination R, which is the angle of refraction, and we also have the adjacent. So if we take cosine of R, cos R will be equal to H, let me use letters first, OG over OF. Please, do we understand up to this point? I'm taking the cosine of the angle of refraction, and cosine is adjacent over hypotenuse. So OG over OF. OG is H. So we have H over OF. OF, we don't know yet. So this is equation 1. Then if we take with the right angle triangle OEF, we have the angle and we also have a letter for the opposite. So if we have the angle, we have the opposite, and the two right angle triangles share a common hypotenuse. So if we take the sine of the angle of deviation, sigma, sine of this will be equal to EF over OF. EF is equal to D over OF. One may ask at this point that, say, why are we determining the sine and not the cosine? We are considering the sine because with triangle OEF, we have the opposite, and then we have the angle of inclination. And then because the two right angle triangles share a common hypotenuse, that is why we are considering the sine. If we take the cosine, we don't know any information about the adjacent to the angle, okay? So we pick the sine because of this information that we have. Therefore, sine of the angle of deviation, sigma, we saw it to be I minus R. So sine I minus R is equal to D over OF. So we have this as equation 2, the same equation 2. Now let's make OF the subject in each of the equations. So please help me make OF the subject in equation 1. Anybody? Help me make OF the subject in equation 1. Yes, Gideon.
So please, will be,
Gideon, I'm listening. OF.
so please, OF will be H over cos R.
Okay, so H over cos of R. Then somebody to help me make OF the subject in equation 2. Help me make OF the subject in equation 2. Saki.
That is, OF will be D over sine I minus R.
Okay, so D over sine I minus R. Good. So we have OF here, OF here. Let's equate them. H over cos R is equal to D over sine I minus R. Help me make D the subject. Help me make D the subject. Yes. Michelle. Michelle, help me make D the subject. Okay, Saki.
So please, D is equal to H times sine sigma all over cos R.
Good. Now, what is the relevance of this? We want to calculate the extent to which the incident ray will be deviated based on the angle of incidence given to you. So this gives us an expression of how the original ray or the part of the ray has been deviated. So take note of this. In most questions with the angle of incidence given, okay, and then the width of the or the height of the prism, you can be asked to determine the displacement. So note that where D, let's define the letters, where D is equal to the lateral displacement of the ray, where H can be the height of the prism, of the prism. And then sigma is the angle of deviation. And R is the angle of refraction. Do not, in using this to find the displacement, you shouldn't also overlook the fact that the refractive index of a material can be determined by Snell's law, sine of I over the sine of R. So we'll be using these two expressions, this one and this one, to calculate for problems concerning refraction of light in rectangular prism. Frank.
Sir, please, I have a question. Does sine I minus R give you sine this one, the angle of deviation?
Yes, I minus R would give you the angle of deviation, not the sine.
Okay, sir.
Okay. Please, is there any other question? All right.
So please, you are good to do.
Okay. Now, let's look at the practical application of this. We can use refraction of light in rectangular prism to determine the refractive index of the material used as a prism. This, please, are you done copying so as to move to the next page? Are you done copying? Class, can I move on?
Sir, please.
Yes,
1 minute.
Yes, please.
Okay, so if you are copying, please hurry up. NSMQ, I think Ghana National and Thomas Aquinas are out of the contest of the whole competition. I think in their
Sir,
contest,
please,
Mangran
any,
as well.
any update on Adisco and Butri along with Pepe?
That will be around 4:30. That will be around 4:30.
Okay, thank you,
All right.
sir.
Okay. Please, can I continue? Okay, so we use refraction of light in triangular prisms to determine the refractive index of a material, of the material used as a prism. Okay, so using refraction of light in rectangular prisms to determine the refractive index of the material used as a prism. These prisms can be made of glass or plastic, perspex. Okay, so we have glass prisms and we also have plastic ones. The plastic ones are often made with perspex. Okay, Gideon.
So please, what is perspex?
Come again.
So please, I was asking, what is perspex?
It's a category of plastics. It's a category of a plastic. So the prisms can be made of glass. So in the lab, we have glass prisms and then plastic ones made of perspex. Okay. So we can quickly conduct a simple experiment to determine the
Sir,
refractive in the, hello.
please, what was the perspex? Like, what are its attributes that it can be an alternative for the prism, the glass prism?
You see, the perspex, as I said, is a category of plastic which is transparent. Okay, and so long as it is of that nature, it can readily allow light to pass through, and it is of that reason that it is used for prisms. Okay, for
Okay.
prisms in this regard, light must be able to pass through it. So because it has that nature, it is of that reason that it is used for making prisms for experiment. So in the lab, what we do is that I think I gave you an overview of this last time, that we have the glass prism, the rectangular prism for that matter. And then what we usually do is that we incident light at one end of it. We incident light at one end of it. Now, this is the incident ray. It can be light from a laser or any other thin source of light. Then two pins are placed on the incident ray, P1, P2. This is the normal. And so this will enable us to measure the angle of incidence. Now it is the images of these two pins are actually traced from the other end. And because light is made to travel from air to the prism, the refracted ray that would bend towards the normal. When it is coming out, the ray is coming out of the prism, the ray certainly will bend away from the normal. So an observer here, watching the images of the two pins, will see the image in this direction. instead of the light going straight, because of the fact that it is traveling through a denser medium, its path will be deviated. And so the new image will be seen along the other side instead. By this, we use this to determine the angle of refraction. So if the images are here, P3 and P4 are here, then you can certainly measure the angle of refraction and also determine the angle of deviation. Okay, now we want to use this to estimate the refractive index of the material used as a prism. So we give ourselves varying angles of incidence, I. So the table of value in this regard has to do with I, maybe starting from 30, 35. The angles can vary. I'm just creating values for the purpose of explanation. So 30, 35, 40, 45, in whichever intervals we want. Now, we trace these images to get the image of P1 and P2 to determine the angle of refraction. So every I would produce a certain R, angle of refraction. So an angle of 30 degrees would give us the corresponding angle of refraction. An angle of 35 will also give us that corresponding angle of refraction. Now, because we are using Snell's law for this, we create a table for sine I, sine of the angle of incidence, and then sine of the angle of refraction. Okay, so sine I, sine R are actually calculated values. I and R are what will be obtained during the experiment. So you measure 30 degrees and then trace the images by viewing through the prism from the other end to get R. You do that for 35, 40, 50, and possibly the last angle that is provided in the question. When you finish, you calculate for sine of 30, then the sine of the corresponding angle of refraction obtained. Please, is there any question here?
Please, can you go over?
All right, so we are using this. I'm just explaining to you how we can, in an experiment, you can use this to determine the refractive index of a prism. Frank, ask your question so that I can quickly explain both or answer both and then continue.
I was going to ask if the angle of deviation will be given, so I find the angle of refraction.
No, in practicals, you are given angle of incidence to find the angle of refraction by measuring I and then tracing the image of P1 and P2 when you view from the other end, okay, A, B, C, D. So you must view through the prism from the side DC in order to put two other pins which will be in a straight line with P1 and P2. So you will not be given the angle of deviation. Sometimes you will be given the angle of incidence or the Granson angle. Please note that the Granson angle is the angle from the prism to the incident ray. So either you are given I or this angle alpha. Frank, are you okay?
Yes.
Gideon.
So how are you going to calculate for the R if only I is given?
Come again.
So how are we calculating for the R if only I is given?
No, by experiment, when you manage to trace the images of P1 and P2 here, upon looking through the side DC, you can be able to draw this line to measure the angle of refraction. I'll send you a YouTube video on this so you relax, okay? So every I would give you a corresponding R. When you finish, these are calculated values. These are calculated values. Practicals, let me talk about the details. You see, in practical works, sometimes in recording our values, there is a need to indicate the least count of the instrument used to measure. For protractors, the least a protractor can measure is 1 degree. So when you are recording values measured by using a protractor, there shouldn't be any decimal point following it. Somebody can mistakenly write something like 30.0. Okay. When you do that, what you are saying is that on the protractor, you can record maybe 30.1, 30.2, 30.3, and so on and so forth. But you can't find that on the calculator. The protractor has a least count of 1 degree. So the angles are exact. So in this case, there should not be any decimal point following values measured from a protractor. If it had been the use of a meter rule, then we can have 30.1, 30.2, because on a meter rule, the least we can have is 1 millimeter or 0.1 centimeter. Please, are you okay? So for the measurement of angles, because we use protractor, it should be exact. There shouldn't be any decimal point. Now, what about sin I? Sin I, sin R are calculated values. These are values we are getting by the use of a calculator. Okay. And in our physics practicals, all calculated values can go for at least 3 dp. So sin 30, for instance, is 0.5. So in recording this, I'm going to record it as either 0.500. It can be more than 3 dp, but at least when we tend to write so much, it is like littering around. So 3 dp, 4 dp will do, but it shouldn't exceed anything 4 dp. You must end at that. Please, are we okay?
Yes, sir.
Yes,
Okay.
sir.
We'll have to echo.
Sir, please, sir, please, you said P1 and P2 are two different, or
They are
like
P1 and P2 are pins, optical pins. That serves as the object. Okay. Object. So this incident ray is a ray coming from these objects P1 and P2. Are you okay?
yes, sir.
P1 and P2 are rays coming from the object. Then P3 and P4 are the images of these two pins as you view from the side DC. All right. So you calculate for sin I, sin I. When you finish, you plot a graph of sin I on the vertical, and then sin R on the horizontal. Please, it can also switch. Okay. It can also switch. It can also be sin R and then as against sin I. Then you plot the values you got for sin I and then plot the values you also got for sin R. Don't forget, you need to choose a suitable scale based on your values of sin I and sin R. Okay. We'll be as we move on, I'll be picking values and then help you in choosing skills and all that. So when you plot your values, your plotted points will be in a straight line. Not necessarily straight, but if they are not, all the plotted points are not straight, you must choose what we call line of best fit. Because you are new to practicals, I wouldn't talk much about these terms, but you choose the line of best fit. Okay? When you choose the line of best fit, you get a straight line. Then you pick any 2 points for the change in the vertical against the change in the horizontal, and you find the slope. This is change in the vertical, which is sine I. Change in the horizontal, which is also sine R. And find the slope. The slope is equal to change in sine I over the change in sine R. This slope must be equal to, this value of slope must be equal to the refractive index of the material used as a prism. Refractive index of the material used as a prism. So if the prism is made of glass, you must have a value close to 1.5. Okay, if it's made of perspex, you must have a value less than 1.5. This is how we can use this to estimate the refractive index of a material, of a rectangular prism. Please, is there any question? If you want me to also throw more light on something, please feel free to talk about it before we move on. So, Eko, thank you. He has given us the meaning of perspex. Perspex is a transparent thermoplastic acrylic resin. Thank you. Alvin.
Sir,
Hello.
sir, please, what's the purpose of the refractive index?
You see, what refractive index of a material is the measure of the material's ability to deviate light. It's the measure of a material's ability to deviate light. So glass, for instance, has a refractive index of 1.5. What it means is that glass can bend light 1.5 times as can be done by air. Okay, so knowing the refractive index gives you the understanding of how that material can deviate or bend light. Please, are you okay?
Oh, yes, sir.
All right. Anita.
Yes, sir, please. I would like to ask how do you trace the images, P3 and P4? How would you be able to trace it in an experiment if they give you an...
Okay. So what you do is that you look at, you see, the glass prism has two parallel sides, AB and DC. You incident light at one side, parallel side AB, and then you view the object. So we are using P1, P2 as the pins. You have to trace the image of these two whilst you look through the side DC. So Anita, you must view from the side DC to place two other pins, which will be in a straight line with P1 and P2. So you must view through DC and then put these 2, 3, and 4 to match P1 and P2. And you can only do that when you view through a side DC. Okay. And I'll send a YouTube video on this so that it will give you an idea of how you can do the viewing. Are you okay?
Yes.
So you relax. I know on paper it's something, but it's not difficult at all. It's easy. Please, is there any other question? All right. If there's no other question, Echo.
Sir,
Mm-hmm.
sir, please, may I ask why we use two sources?
You see, we want to trace images, okay, and we'll get the line. You see, we'll be ruling lines. We'll get it better when we use two pins or two objects, what you are calling our sources. If we use one, we may not get the line properly. Imagine if I have to draw an incident ray and I'm only drawing the ray from only one point. But if I have two, I can combine, or I can join the 2 points better to give me a better line. So that is why we use two. Are you okay?
Please, the line wasn't.
What I'm saying is that for the sake of accuracy, that is why we use two things, okay, or what you are calling as two sources. Is for the sake of accuracy of our measurement. Are you okay?
Okay, sir.
All right. I'm going to send a question quickly on the page. Give me a minute to upload it so we can quickly learn how to apply this concept in solving of questions or problems. Just a minute to upload the. Okay, so I've taken short of it, but I think network is uploading it on the platform is taking some time because of network. So we'll continue, and then we can even later use that as an assignment. Okay, it will be you can solve it as an assignment. Now let's look at another area under refraction: real depth, and apparent depth. Real depth and apparent depth. Whenever you place a coin or you create a mark and then place a glass block on the mark and you try to view from the glass block, you make a very interesting observation. So assuming this is a paper and then you create a mark on the paper, then you place a glass block or a glass prism on the paper. Then you try to view the image of this. you make a very interesting observation. Or when you fill a bucket of water and then you place a coin under it, and you try to observe or look at the coin in the water, it also gives you a very funny observation. When you place a pencil or pen in a cup with water, and then you try to look at the pen or pencil at the interface between the water and then the air, it always gives you a very funny observation. Please, can you share with me what are the nature of observations seen in these scenarios I earlier talked about? When a coin is placed in water, when a pencil and all that. Yes, a contribution from any one of you. Okay, Gideon.
So please, when the coin is placed in water, you get to see a wavy image. Like the image is not stable.
The image is not stable.
Yes, so it's kind of like moving. It looks wavy.
Really? Okay, more views. I see you do Bwedi. What's doing?
Please, when you place a coin at the bottom of maybe a pool or something, the bottom appears closer to your eyes.
Exactly.
Or you see
the bottom, the coin appears closer to you. More views. When you create, okay, a spot on paper, and then you place a glass block on the spot, and then you view through the glass block, what do you usually see? Anita? Okay, Frank.
It looks like the spot is inside the glass block.
The spot is inside the glass block, or the spot is closer, okay, closer to the viewer, or it's been moved up than its real position. Let's use ray diagram to understand what happens. So we have, this is glass containing water. Then a spot is created here, and an observer, either up or at the side, wants to look at the spot. Let's see how you can use ray diagram to explain whatever is happening. Fishes in rivers, in ponds, cannot easily be caught due to this. If you happen to stand closer to a pond or an aquarium, and then you want to just catch fishes within, if you are not experienced, the chances that you can easily miss them is very high, because whilst you look through the pond or the aquarium, where you see as the position of the fish, in reality, that is not it. It is far away than what you think. So you push your hand to that position and you can easily miss that. So that observation is as a result of what we are coming to discuss, the real death and then apparent death thing. So this is water in a basin. Angie, stop writing on my board. So we see as a result of light, reception of light from the source. Okay, so if you are outside, if an observer is here, I want to look at the position of the coin. Light must first come from the object to be received by your eye. Okay, so let's only draw two lights coming from different angles from the object. So a ray of light traveling from the object in that parallel manner to the boundary or the surface of the water would go undeviated. So whenever light travels perpendicular to a plane, it goes undeviated. So this light from the object would go undeviated. A ray of light from the object traveling at any other angle apart from 90 must be deviated. So an arrow to indicate. Once this is the boundary or the interface separating water and then air, we must draw a normal there. So this is a normal. Because the light ray is from water to air, at the boundary, at just this interface, it will deviate away from the normal. And then be received by the observer. So this becomes the refracted ray. Okay. Now when we trace back the original part of the refracted ray, let's trace it back. Where the ray appears to meet the first ray becomes the apparent position of the image. So it means that an observer watching this object O from the side will see the image to be here. This becomes the image. So the observer would see the object as if it is closer. Meanwhile, what he's seeing is not the real position of the object. It's an optical illusion. And this is the reason why if this had been a fish, the chances that you will miss it is very high, because what you are seeing as the fish is not in reality a fish. It is an optical illusion. Is that okay? So this therefore becomes the image of the object. So O is the object and I is the image of the object. This is what as an observer you will see, not the real life situation of the object. Please, is there any question? Is there any question? Okay. Now, the distance from the water surface to where the object is the real depth. So the real depth is actually the actual depth or height. So this is RD. The distance from the surface to where the image is becomes the apparent depth. The apparent depth, AD. So this depth is measured from the surface. Take note. It is not from the object. So from the surface where the object is the real depth. From the surface to where the image is the apparent depth. So where RD is equal to the real depth, and then AD is equal to the apparent depth. Saki.
Sir, please, could you take the apparent depth again? I didn't really hear that, please.
Apparent depth is the height from the surface of the water or the liquid to where the image is. This is the image. I is the image. O is the object. So this is, to an observer, this is what it will be seen. So that distance is the apparent depth. Okay. Now, if we subtract the apparent depth from the real depth, it gives you what we call as the vertical displacement, or simply the displacement. So this is D. So the displacement is equal to the real depth minus the apparent depth. So D is equal to RD minus AD. You can also use this concept to determine the refractive index of the liquid. You can use this to estimate the refractive index of the liquid. The refractive index, absolute, refractive index of the liquid, therefore become the ratio of the real depth to the apparent depth. Please, are we okay? Class, are we okay? Michelle, Anita, and Co. Are you fine?
Yes, sir.
The girls, let me hear from you.
Yes, please.
Janelle, are you there?
Yes, please.
Okay. So let's assume the observer this time doesn't view from the side. Joshua. Frank, you are not exhausted. We'll finish soon. Joshua, go ahead.
Sir, please, I want to know what the N is representing.
N is the refractive index. Okay, let me define it. N is the refractive index, absolute refractive index. Index of the liquid. Of the liquid. So if you want to estimate the refractive index of the liquid, is the ratio of the real depth to the apparent depth. Assuming the observer this time views from above, directly above, not from one corner. So this is the eye of the observer. Lordina, are you here?
Yes, please.
Okay. So the same thing. This is the surface of the liquid. The observer is doing the viewing from the surface of the liquid. A ray of light coming perpendicular to the surface goes undeviated. So it will be picked by the observer. No trouble. A ray of light traveling at an angle will be deviated. And since the ray is coming from water to air, it deviates away from the normal. Away from the normal. Another ray from the object, there can be imbrukutu billions of light rays coming from the object. So let's draw another normal. This will also bend away from the normal. Since there are rays, an arrow to indicate that there are rays. Now, if we retrace the original path of the refracted ray, where they appear to intersect the other ray, will be the position of the image. So the image I will be here. Object is here, image is here. So if the observer is observing from above, this is how he sees the image of the object. Still, the real depth is the distance from the surface of the liquid to the actual position of the object. This is RD. The apparent depth is the distance from the surface to where the image is. Apparent depth. So these are the two possible ray diagrams that can be drawn from this. Are you okay? Please, is there any question? We have about 6 minutes to end the show. So if Echo,
So please, you said when a viewer views from above, so they see the actual depth, right?
Echo, I'm not getting you.
So you said when a viewer
Yes,
views from directly above or
yes,
perpendicular to the
the
object. Okay.
object. Are you okay?
Yes, sir.
All right. Please, is there any other question? All right. I'm taking our last attendance list. Some of you are gone. Yes, your hand is up. Go ahead. Hey, I can't mention your name. Can you help
Sir,
me?
Capicas.
Come again.
Capicas.
Okay, capicas. Okay.
Sir, please, what's the difference between the apparent and the real depth?
The apparent, you see, the image is virtual. It's not real. So it appears the image is there, but it's in actual sense it's not there. That's why we call this an optical illusion. Okay. So the apparent depth is the distance from the surface of the liquid to where the image appears to be. And then the real depth is the distance from the surface of the liquid to where the object is actually is. Are you okay with the difference? Hello, are you okay? All right.
Yes, sir.
Okay, so class, if you don't have any question, my time says we have 3 minutes to end. Echo,
Sir,
Aria, Frank is exhausted.
sir, please, can you tell me the real life applications using such this theory?
Come again.
Applications from this theory.
Of this.
Yes, sir.
We discuss the applications. That is, when you visit a pool in a sunny afternoon and you look at the beneath or the underside of the pool, it always appears to be shallow than it actually is. This is where you find an application. Then when you place a block, even a hand lens, if you place a hand lens on a mark or a coin and you view through it, it always appears to be magnified. That magnification is due to this. You see, when you look at writings, whenever you are wearing glasses, you see a magnified something. But in actual sense, what you are seeing is not magnified. So if you look at somebody and then you see the person's head to be so big, when you take off your glasses, the person's head is not big. So it's an apparent situation. That is also an application of this. Are you okay? So that
Yes, sir.
optical illusion thing, the optical devices like lenses, prisms gives us, that is what we are discussing as the concept of real depth and apparent depth. Okay. All right. I'll send the applications of the prisms to you, rectangular prism. Please put it down as part of your notes. Okay. I'll forward the question I wanted us to solve under this concept to the group. Try it. And today even ends our physics meeting. So it will be an assignment for the week. But I'll load it a little bit, maybe 2-3 questions, so that it can actually oscillate our brain. This is where we draw the curtains on today's meeting. Please, if you are new, if you are joining us first time this semester, please, whenever you visit the YouTube page, subscribe and then share and then pass your comment. It will help develop the channel. Okay, do that for me because I need it so badly. And do not hesitate to recommend us to your colleagues who are perhaps at home wanting Capricorns.
Sir, please. So, what will be our next meeting topic so that we can revise,
We'll look at refraction of light in triangular prisms. We have
Okay,
to
sir.
finish the prisms. And when we finish, we'll look at lenses. And for optical instruments, I'll leave it to you. If you want us to treat optical instruments, fine, we'll do it. If you want us to move on to thermometers, temperature, we can equally do it. So, but I'll treat refraction of light in triangular prisms, lenses, and then you decide whether we should treat optical instruments. Okay, so that'll be it for next week. Until then, may the good Lord be with you. Take care of yourselves and please revise. Bye-bye.
Bye.
Okay.
Bye. Tip, but will you put the recorded class onto the group?
Definitely.
Thank you, sir.
Welcome.